Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. This reaction involves a cyclopropylmethyl tosylate system undergoing E2 or solvolysis elimination under basic conditions with heat. The substrate is 1,1-methylcyclopropyl cyclohexyl tosylate, where the OTS and the spirocyclopropane bearing a methyl group are on the same carbon, C1, of the cyclohexane ring. Moving on to the next step. The molecule has a quaternary carbon, C1 of cyclohexane bearing 1, the cyclohexane ring, 2 OTS, leaving group, 3, a cyclopropane ring with a CH3 group, spiro junction. The OTS is on a wedge-dashed bond indicating stereochemistry. Moving on to the next step. Under Ho strong base and heat, delta, the tosylate acts as a leaving group. The cyclopropyl carbonyl system, cyclopropane adjacent to the carbon-bearing OTS, is prone to ring opening. When OTS leaves, the cyclopropane ring opens to give a homoallyl allylic carbocation, or the base assists in an E2 type process with cyclopropane ring opening. And for the final step, the ionization of OTS gives a cyclopropyl carbonyl cation at C1 of cyclohexane. The cyclopropyl ring opens to give a homoallyl cation. Specifically, the bond of the cyclopropane ring between C1, spirocarbon, and one of the cyclopropane carbons breaks, placing the positive charge on the ring-opened carbon. This generates an allylic system within the cyclohexane ring. When the cyclopropane, bearing CH3, fused at C1 of cyclohexane opens, the methyl-bearing carbon of the cyclopropane becomes part of an endocyclic double bond. The ring opening incorporates the cyclopropane carbons into the cyclohexane ring, expanding it, or alternatively, the cyclopropane opens to place the double bond endocyclically. Given the spirocyclopropane at C1, opening of the cyclopropane bond between C1, cyclohexyl, and the CH2 of cyclopropane, not the CH3, gives a carbocation stabilized by the adjacent CH3 bearing carbon, leading after deprotonation to 1-methylcyclohex-2-Na, option B. The cyclopropyl carbonyl cation rearranges opens to give the most stable alkene. The endocyclic trisubstituted alkene, 1-methylcyclohex-2-Na, is more stable than the exocyclic methylcyclohexane, option C, or other less substituted alkenes. Option A would require a different connectivity. Option D is a less substituted product. The homoallyl rearrangement from the cyclopropyl carbonyl cation followed by loss of proton gives 1-methylcyclohex-2-Na as the major, more stable Z7 product. Why other options fail? A. 1-methylcyclohex-1-Na would require the methyl to be directly on the double bond carbon in a specific way not favored here. C. Methylcyclohexane is an exocyclic less substituted alkene, less stable. D. 4-methylcyclohex-1-Na would require methyl migration far from the reaction center. Therefore, the correct answer is B. Therefore, the correct answer is option B.